Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Modulated Field Effect Transistor MODFET from the paper Semiconductor Materials and Devices. So let us see what we are going to learn in this module. First, the structure of MODFET along with the fabrication and operation will be discussed. Second, various characteristics of MODFET will be discussed along with its advantages and disadvantages. So, students, let us start with a basic introduction about the module. Modulation doped field effect transistor MODFET is a heterojunction device which has the desirable properties of high speed operation and low power dissipation. MODFET is also called as High Electron Mobility Transistor HEMT or Two-Dimensional Electron Gas Field Effect Transistor or Selectively Doped Heterojunction Transistor SDHT. Frequently, it is referred to as by a general name HFET, or we can say heterojunction field effect transistor. The unique feature of the MODFET is the heterostructure in which the wide energy gap material is doped and carriers diffuse to the undoped narrow energy gap material where the channel is formed. So the net result of this modulation doping is that the carriers in the undoped hetero interface are spatially separated from the doped region and have extremely high mobilities because there is no impurity scattering. Carrier transport parallel to the layers of the superlattice was first considered by Isaki and Su in 1969. The development of MBE and MOCVD technologies in the 1970s made heterostructures, quantum wells, and superlattices to be practical. So, Dingle et al. Was a scientist who first demonstrated the enhanced mobility in aluminium gallium arsenide modulation doped superlattice in 1978. Stormer et al. Subsequently reported a similar effect using a single aluminium gallium arsenide heterojunction in 1979. This effect was applied to field effect transistors by Mimura et al. In 1980 and later by Delagabedov et al. In the same year. Since then, the MODFET has been the subject of major research activities and promises to be an alternative to MESFETs for high-speed circuits. Structure of MODFET. The structure of a typical MODFET is shown in this figure. So as you can see over here, there are 4 layers in this structure: an intrinsic gallium arsenide buffer layer, an undoped aluminium gallium arsenide spacer layer, a doped aluminium gallium arsenide donor layer, and lastly the cap layer. So there are 2 ohmic contacts and 1 gate electrode for providing the electrical connections of the transistor. MODFET works on the principle of modulating the concentration of a two-dimensional carrier gas by a gate potential. The most basic construction of a MODFET consists of the active region, which is generally N-type, which is grown on the top of an undoped buffer layer having low band gap. This precedes the growth of high band gap doped material. So students, consider the example of aluminium gallium arsenide MODFET, in which the formation of electron gas is due to the diffusion of the electrons donated by donors in N-type aluminium gallium arsenide to the lower band gap gallium arsenide. So now the donors are set back away from the interface in order to increase the low temperature electron mobility. This further leads to a reduction in Coulombic interaction between the electrons in the electron gas and donors in aluminium gallium arsenide. This setback layer formed is referred to as the intrinsic layer. Enhancement in electron confinement can be obtained by raising aluminium arsenide mole fraction in aluminium gallium arsenide, which leads to a large discontinuity in the conduction band between the gallium arsenide and aluminium gallium arsenide. So another way of electron confinement from the substrate side is by exploiting an aluminium gallium arsenide layer between the electron sheet and gallium arsenide buffer. So the resultant discontinuity in the conduction band at heterojunction interface, resulting in the confinement and localization of those diffused electrons in the material having low band gap, determines the number of electrons that can be sustained at the interface, which is referred to as the two-dimensional electron gas 2DEG, which is clearly explained in this figure. When the gate voltage, as shown in this figure, is made sufficiently high, leading to the state when the source drain channel is no longer depleted. At this instant, the 2DEG is free to conduct in the undoped material. Since the undoped material has no added extra donor atoms, impurity scattering no longer inhibits the carrier mobility and saturation velocity. Consequently, it is also known as the Hall mobility is limited only by phonon scattering, and the conduction mobility is equal to the Hall mobility due to degeneracy in gallium arsenide conduction band. So the spacer layer which is formed leads to the rise in the channel mobility by shielding the 2DEG from ionized impurities. So now regarding the electrical contact, two ohmic contacts are provided on the surface of the source and the drain, and a Schottky gate contact is used to modulate the current flow between these two ohmic contacts. In general, major refinements of MODFET following its invention have centered around improving the electron transport properties. So, students, many studies have been done on N-type MODFET devices, and the main component of MODFET is the specialized PN junction present inside it and consists of a junction that uses different materials for either side of the junction. So from this figure, the buffer layer, which is generally gallium arsenide, is epitaxially grown on the substrate in order to isolate the defects from the substrate and to create a smooth surface upon which to grow the active layers of the transistor. Now let us discuss the fabrication of MODFET. While fabricating MODFET, firstly an intrinsic layer of gallium arsenide of 1 micron thick is deposited on the semi-insulating gallium arsenide layer. After this, a very thin layer of aluminium gallium arsenide of 30 and 60 angstroms thick were deposited in order to introduce the separation between heterojunction interface and the doped aluminium gallium arsenide region. The doped layer of aluminium gallium arsenide up to 500 angstroms thick is deposited above the layer, and its thickness needs to be precise, which in turn requires special techniques. There are two main structures that are generally used. That is, first is self-aligned ion implanted structure and the other is recess gate structure. The electrodes, mainly gate, drain and source, they are made up of metallic contacts in the self-aligned on the ion implanted structure. Sometimes source and drain contacts may be made from germanium and gate contact is generally made from titanium, forming a small reverse biased junction similar to that of gallium arsenide FET. In the case of recess gate structure, a new layer of N-type gallium arsenide is introduced to fabricate the drain and source contacts, and selected areas are etched. So the thickness of the layer under the gate is highly important in deciding the threshold voltage of the FET. So, towards aiming this, the size of the gate and the channel is kept to be very small. The typical thickness of the gate is only 0.25 microns or less than this, which is beneficial for the device to have a very good high frequency performance. So students, let us now discuss the operation of MODFET. The operation of the MODFET is slightly different from other types of FET, and it is able to give improved performance over the standard junctions or MOSFETs in particular in microwave radio applications. There is a movement of electrons from the N-type region through the crystal lattice, and many of them remain close to the heterojunction. These electrons form one layer thick, forming a two-dimensional electron gas where the electrons are able to move freely. So this is due to the fact that there are no other donor electrons or other species with which the electrons will collide, and thus the mobility of the electrons in the gas is very high. So a voltage bias applied to the gate leads to the formation of a Schottky barrier diode, which is further used to modulate the number of electrons in the channel formed from the 2D electron gas. So this in turn controls the conductivity of the device, which can be compared to the more traditional types of FET, where the width of the channel is changed by the applied bias at the gate. Characteristics of MODFET. From this diagram, we can conclude that the gate bias at which the channel starts to form between the source and the drain occurs when EF at the gallium arsenide surface coincides with EC, and it is given by Vt equal to phi Bn minus Vp minus delta Ec by Q, where Vp is the pinch off voltage for the aluminium gallium arsenide, and it is given by Vp equal to Qnd chi d square divided by 2 epsilon s. Now by varying chi d, Vt can be varied between the positive and the negative values. So with a gate voltage greater than or larger than the threshold, the charge sheet induced by the gate is capacitively coupled and is given by Ns equal to C naught multiplied by Vg minus Vt minus psi x by Q, where C naught equal to epsilon s by chi d plus chi ud plus delta d, where chi d and chi ud are the doped and undoped aluminium gallium arsenide thickness, and delta d is the channel thickness of the two-dimensional electron gas, estimated to be approximately 80 angstrom. Psi is the channel potential with respect to the source, and basically with respect to the source, and it varies from 0 to the drain bias Vd. So the drain current at any point along the channel is given by I equal to W mu n Q n s epsilon x, which is equal to W mu n C naught multiplied by Vg minus Vt minus psi x multiplied by d psi x by dx. Since the current is constant along the channel, so integrating this equation from source to drain, we get I equal to W mu n C naught by L multiplied by Vg minus Vt, this is multiplied by Vd, minus Vd square by 2. Now the variation between the current versus Vd is shown in this figure. In the linear region, above equation reduced to an ohmic equation, and I linear is equal to mu n C naught W multiplied by Vg minus Vt multiplied by Vd divided by L, and the transconductance is Gm, that is for the linear portion, equal to d I linear divided by dVg equal to mu n C naught WVD by L. So at high VD, Ns at the drain is reduced to 0, corresponding to the pinch-off condition, and the current saturates with Vd. And this saturation current, Vd saturation, or the voltage, equal to Vg minus Vt, and I saturation equal to mu n C naught W by 2L multiplied by Vg minus Vt the whole square, and Gm saturation equal to Di saturation by dVg equal to mu n C naught W multiplied by Vg minus Vt divided by L. So students, let us now discuss the reliability. Reliability of MODFET is an important parameter which is affected by the epitaxial structure, device fabrication, and device geometry. There is one drawback of using AlX gallium 1-X arsenide in the material structure is the occurrence of traps called as DX centers for AlX arsenide mole fractions around x equal to 0.25. So these traps are deep donor levels which can cause reduction in drain current, enhancement in low frequency noise, and photoconductivity. This further creates problems, particularly at low temperature. Further, the creation of DX centers increases with higher doping of the AlX gallium 1-X arsenide. This formation of DX centers can be controlled by keeping the AlX arsenide content below x equal to 0.24 for N-type doped AlX gallium 1-X arsenide. A second possible reliability problem that can occur is the deconfinement of the two-dimensional electron gas 2DeG under high temperature conditions. So thermally accelerated testing has shown that aluminium can migrate laterally into the gate, resulting in a change in the conduction band discontinuity. So the advantages of MODFET are: first, have high gain, making them useful as the amplifiers. Second, have high switching speeds, which are achieved because the main charge carriers in MODFET are majority carriers and minority carriers are not significantly involved. Next is the MODFETs have low, extremely low noise values because the current variation in these devices is low compared to other FETs. Lastly, when it is compared to MESFET, MODFET can tolerate higher gate bias due to higher barrier of aluminium gallium arsenide. Let us now discuss the applications of MODFET. MODFET was originally developed for focusing on high-speed applications due to its transconductance, and it is the first device to have a very low noise figure. This is related to the existence of 2D electron gas and the fact that there are less electron collisions. Due to their noise performance, they are widely used in low noise small signal amplifiers power amplifiers, oscillators, and mixers operating at frequency up to 60 GHz and more. And it is anticipated that ultimately devices will be widely available for frequencies up to 100 GHz. The devices based on MODFET, they are used in a wide range of RF design applications, including cellular telecommunications, direct broadcast receivers, DBS, radar, radio astronomy, and any RF design application that requires a combination of low noise and very high frequency performance. MODFETs, they are also manufactured by many semiconductor device manufacturers around the globe, which may be in the form of discrete transistors, but they are generally exploited in integrated circuits nowadays. The chips based on MODFETs are called as monolithic microwave integrated circuit chips, MMICs, which are widely used for RF design applications. Also, the speed of MODFET circuit is about 3 times faster as compared to MESFET. Commercially available MODFETs generally operates at frequency higher than 60 GHz with channel lengths ranging between 0.25 micron and 0.5 microns. Some examples of analog applications are low noise, small signal amplifiers, power amplifiers, oscillators, and mixers. For digital circuits, high speed logic and RAM will be useful for high speed computers. So students, let us summarize what we have learnt in this module. First, the structure of MODFET along with the fabrication and operation was discussed. Second, characteristics of MODFET were discussed. Third, the advantages in terms of reliability and applications were discussed in detail. Thank you.